So yes, this is a similar to a presentation I have done before. So if you went to a presentation on seismic analysis of nuclear structures, you might see a bit of repetition. So apologies for that, but hopefully there's some new stuff as well. And this talk is more focused on conventional structures. Just to start then quickly, I've got a lot to cover. About me, so a chartered civil and structural engineer. About a third of my career has been in conventional structures. The last 12 years have been in nuclear. Worked for various companies on a lot of very cool projects. I think some of them are on this slide. In my first 6 years, I did many different cool projects. In the last 12, I've done like 2 projects. But anyway, that's the nature of nuclear. But yeah, it's two pretty cool projects. So in this talk, only have an hour. I mean, I want to try and have cover it in 45 minutes and then have some time for questions. It's a massive topic. There's just I can only really touch on a few things. So my focus in this is to try and think of what are the main fundamentals someone starting out in seismic analysis should know, and hopefully, if you can understand a couple of basic concepts, you'll have the confidence to talk, to understand what's going on, and to talk to people about what options are, and then obviously you can do further research in your own time. So that's what I want to do. Very little maths. It's unavoidable to have some maths, but we'll see how it goes. And I'm going to start with very simple, and then we'll go to simple, and then hopefully we'll stay around simple for the talk. But this is the very fundamental, just to get us kicked off and make sure that everyone feels confident in themselves. Oh, I know what this is. I can follow this. So easy start. What's an earthquake? Well, it's the sudden release of stress in the Earth's crust. So the Earth's tectonic plates are constantly moving. If they can move freely, that's fine. We don't get earthquakes. Where something prevents that movement, it causes a buildup of energy. So if 2 plates are trying to rub together and there's some interlock which prevents that, they'll keep trying to move. The energy will increase. Eventually, the energy that's built up will exceed what's blocking it, and it will suddenly give, and there'll be a release of energy. And that's generally what we're talking about with what causes the earthquakes. And there's various kinds as shown in this slide, and it's all about how the plates are moving relative to each other. If you look at recorded earthquakes, you will find, if you look at all recorded earthquakes, you will find that you get most recorded earthquakes where people are doing more recording. So you'll get a huge amount of recordings in developed countries and less away from that. So a more useful tool to look at is where the large earthquakes occur. So this particular plot is showing earthquakes of magnitude 6 or greater. And what you again, just recorded earthquakes, like there'll be more around in the less populated areas that we don't know of. But just what you can see is if you have to join the dots, do a nice join the dot exercise like we did as kids, you'll basically draw out the tectonic plates, and that's because the large earthquakes, the big events, generally occur at the boundaries. And you can see that this specific ring of fire, as it's known, basically down the west coast of America, then up New Zealand, in the east, Southeast Asia, then Japan. That is a very active zone. There's lots of the biggest earthquakes occur in that area. But anyway, it's generally at the boundaries of plates, and you can see in the UK we are nice and safe in the middle of the Eurasian plate, or not quite in the middle, but away from the edges, and no real significant earthquakes recorded. In terms of earthquakes, we define them in terms of moment magnitude. You might have heard of the Richter scale. The moment magnitude is considered more accurate, but they're very similar. Both are logarithmic. Going up in moment magnitude, going from 1 to 2 is because it's logarithmic. 1 to 2 is a very small difference. Going from 8 to 9 is massive. It's a massive increase. So it's about 10 times the magnitude and about 30 times the energy for each step up in magnitude you have. And for comparison, if you think of maybe in the Britain, we might get around a magnitude 5 every, I don't know, 20, 30 years. And you consider Fukushima was magnitude 9. It's like 9 to 5. Oh, that's not that big. That's around 1 million times difference in terms of the energy released. So like I say, this logarithmic scale, when you get to the high numbers, even small changes like 0.1 are quite big. If we look quickly at the UK, I mean, we do get earthquakes in the UK. Like earthquakes can occur from a number of sources. And this diagram on the screen, the red dots are actually recorded, the yellows are estimated. So it's, you know, Mrs. Smith felt her plates shaking on the shelf, and various other people in the village felt the same, and they give a description of that, and based on that we try and match a magnitude to it. So it's an estimated value, whereas the reds are recorded. But we do get earthquakes spread out all across the UK. Generally, they're not that big. I think the largest believed earthquake that we've recorded is 1931. But again, this is an estimated one, so it's like based on you know, verbal accounts of how people felt, and it only caused minor damage to some of the buildings on the east coast of England. So in the UK, we're generally talking around this frequency. So between 5 and 6, maybe every 10 to 20 years. And in terms of that magnitude 1 to 2, we actually get quite a lot of them, but nobody notices. It's just this. The seismic equipment will record it. It's difficult to say anything about frequency when we get to magnitude 6 because we just don't have sufficient records to assign anything statistically to it, but they are rare. So that's our easy start. What earthquakes are, generally due to tectonic plates moving. We get the biggest ones at the edges, and in the UK we are generally low magnitude, even though we do get maybe get a reasonable number. They're not of particular concern. And if you look at the Eurocodes, Eurocode 8, which covers seismic design of buildings, the UK National Annex to Eurocode 8, the forward to that basically says, don't worry about it in the UK. So there's a whole code, and then we just have a statement, don't worry. So yes, it's not an area of considerable expertise in the UK because we don't generally need to consider it except for special cases like nuclear. So okay, that's our easy start. Hopefully now we know what an earthquake is. So I want to talk about how we represent earthquakes, and there are basically two ways that are commonly used in structural design of buildings. And the first is a time history, and the second is a response spectra. And they're both representing slightly different things, but they both are a representation of an earthquake. And the time history is a representation of the earthquake itself, and the response spectra is a representation of the response. But we will cover that just now. And I'm going to start with time history, because even though that's a more complicated analysis, it's actually, I think it's quite easy to understand. So if you were to give this to a non-engineer, I think they could still understand that we have time on the x-axis, we have acceleration or some other measurement, which can be velocity or displacement on the y-axis, and we see how this varies with time. And obviously, in the periods of high intensity shaking, we get higher values, going backwards and forwards, and I think we can intuitively understand what this is. This is an earthquake. Ground shakes one way, then the other, one way and the other, and it varies with time. Hopefully straightforward. So that's starting again with something easy. Time history is like this. It's a plot of acceleration or velocity or displacement with time. You generally, it's plotted in terms of acceleration, sometimes displacement, quite rare to use velocity. But yeah, you can do either, and you can from one you can calculate the other. Obviously the acceleration is the rate of change of velocity, the rate of change of displacement. So by differentiating and integrating each, you can transform them. It's a single event. So this is a very specific earthquake that is measured there. It's just one event. And we have 3 of these for any one earthquake, covering the 3 orthogonal directions. So there'll be one east-west, one north-south, and one vertical one moving up-down. So any single earthquake will have 3 time histories representing these 3 components. And we can get them by measuring an earthquake. We have computer software that can artificially generate them. And most commonly, it's a combination of the two, where we take a real earthquake base input and then adapt it for use on a specific site, because like maybe the earthquake's from California and it's completely irrelevant to the UK, but we can scale it up and down. We can amend the frequency content to try and match a particular response we're trying to replicate in the site we're of interest. So it's, yeah, that's time histories, and generally this is how we get them, this combination. So I think hopefully that's easy, or at least easy to follow. Intuitively, you understand what time history is. Response spectrum is less so. I think when people see a response spectrum, they don't know exactly what they're looking at. Is how does that really represent an earthquake. So I'm just going to try and cover that a bit now, and hopefully you'll understand it a bit better at the end. First thing to say, though, is you'll see response spectra plotted in terms of frequency or in terms of period. This is the same response spectra plotted, one in terms of frequency, one in terms of period. That is simply, it's the same information just on against two different scales. Period is 1 over frequency, or frequency is 1 over period, whatever you want to look at it. So they're reciprocal of each other. This is not time here, even though you see seconds. This is a property of the system. So the system will have a fundamental frequency. It will have a period associated with its response. This is a property of the system. It's not time on this axis. So what it is it's a plot of the peak response. This is important. It's only showing the peak response. So time history, you've got the whole response. In response spectrum, you're just plotting the peak. But it's a response of a peak response of a single degree of freedom system for a specific damping level to an input earthquake. So we still have a time history that this response spectrum is based on. This response spectrum is representing the same information as would be in a time history, but less information. It's only representing the peaks, but it's giving how the peak response varies with the frequency or period of the supported system. And in this case, it's a 1 degree of freedom system. So again, we'll have 3 of them: north, south, east, west, up, down. And like I say, there's much less data in here, and it makes it easier to use. And we get them from, well, generally they're given in codes. So this particular spectra is a nice smooth line, as you can see, very, very nice. It's a code when it's from the European Utilities Requirement Code, which is used for a lot of design of energy buildings. You can do a very specific site assessment. We call it a probabilistic seismic hazard assessment, which is what we do in nuclear, where we actually look at details of the site, what faults are around it, looking at the soil properties, and we derive a very specific response spectra for the site, whereas the code ones are quite generic and supposed to bound many cases. Or we can generate it from a time history. And I want to have a quick look at how we would generate a response spectrum from a time history, because I think that will help you understand what a response spectrum is, because I've tried to explain it here, but I still think people might be wondering exactly what this means, a plot of peak response. And I think if we look at taking a time history and turning it into a response spectrum, you'll be able to understand better what a response spectrum actually is. So this is a little bit of maths, but hopefully we'll keep it reasonably straightforward. So we're starting with the simplest thing we can have, which is a single degree of freedom system. So this mass, for the purpose of this example, can only move vertically. So that's the single degree of freedom. We have a base support, which is going to have an input motion assigned to it. And the mass is connected to this base via a stiffness, a component with a stiffness, and it also has damping associated with it. And this is the equation of motion: mass times acceleration, velocity damping, and stiffness times displacement is equal to the input motion. And we have to solve this equation. So that's as simple as we can do. But, if you forget about the maths, basically we're going to shake the support, and we're going to measure the response, how the mass moves, and it's going to move differently to the input response. That's what we are doing with our, that's the basic model we're using to generate a response spectrum. But we're going to make it even simpler. So first of all, we are going to fix the damping at a set value, because if you maybe remember what I said, a response spectrum is associated with a particular level of damping. So to create a response spectrum, you need to choose the damping level. And then you generate a, say, 5% damped response spectra. Or if you pick the damping at 7%, you generate a 7% damped response spectra. Because the response spectra is the response, it has to consider the properties of the system, and one of the properties is damping. So we're going to set the damping to 5% in this example, and we don't need to consider it anymore. And we have this extremely even easier system now. So we have a base support. It has an input motion. There's a mass which is going to move, can only move vertically, and there's a stiffness between the two, and the damping is constant. So we don't need to consider it here. And basically what happens is, like I said, we shake this bottom part vertically only. The mass moves, or has again, displacement, velocity, acceleration. Let's say acceleration accelerates with a different response, and we measure that. And that is our system for generating a response spectra. So from this hopefully simple system, which you should I'm hoping you can follow. We're going to extract just two pieces of information, and they are two very simple pieces of information. The first is we're going to extract the frequency of this system, and that frequency is this. Sometimes you'll see F for frequency or omega for the fundamental period of vibration. It's simply root K over M, so root of stiffness over mass. So this stiffness is a defined value, the mass is a defined value, 1 over the other, square root of it. That is the frequency of the system. And that's the first thing we're going to take from this. And the second thing we're going to take is the peak of the response. So from this response we've measured with time, we're going to take the maximum acceleration value over the full time length. And it doesn't matter, this is the absolute value, so it doesn't matter if it's positive or negative, we're just taking an absolute value, that we're going to extract that. So we have these two outputs, and we plot one against the other. So for this, I'm not putting any units or values on this, but basically for this frequency, this particular frequency of this system, there is a response, and the peak value of that response, let's say acceleration, the peak acceleration of that response is a set value. And that is the start of our response spectrum. And then we're just going to do this multiple times for multiple frequencies. So this is the same model. We have a mass, we have a stiffness with a frequency associated with it. We have the same input. We're just using it's the same input each time. And for each system, this is not a single model. This is multiple small models. So we'd run this case, then we'd run this case, then we'd run this case. We are changing the mass in each case. So reducing the mass. The frequency is root K over M. So we are increasing the frequency. The stiffness stays the same. I mean, alternatively, you could amend the frequency. What's important is the ratio between the two. So you amend the ratio between the stiffness and the mass to adjust the frequency, and you get a different response. So for example, this one, omega 1, or frequency 1, we have a response, we take the peak of that, and we plot it against omega 1 on the frequency axis. And then we have a different system with a different frequency. It has a different response, and we take the peak of that, and we plot that against this, and we have a third system, different response, blah, blah. And you can do this an infinite number of times. Obviously, there's an infinite number of frequencies you can use, but basically you get enough, and you join the dots up, and that is your response spectrum, essentially. And what it means is that for what you're saying is, if for my particular earthquake input, so this time history input, for the input, if I have a 1 degree of freedom system with a frequency of 10, the maximum acceleration I will get, I don't know when it occurs, I don't know how long it occurs, I don't know anything about its occurrence, but I know the maximum value will be, in this case, 0.65, or if I have a frequency of, say, 30, it's 0.25. So if you have a single degree of freedom system with a particular frequency, this tells you what the peak response of that will be. And you've lost all the other information. You don't know anything about when it happens in time, but you just have the peak. So that is what a response spectrum is. I'm hoping that kind of going through that exercise, you can kind of better understand what it is. It's representing the response of a system to a particular input. It's the same input as the time history. It's just represented a different way, represented in terms of the response. Now, one other thing on response spectra, this nice shape, which I've used multiple times, like I say, is fairly common. We can divide it into 3 zones. And for all of these, for this response spectrum, I'm using this particular input. This is the input at the ground level, or in my example is actually at the top. I've switched everything around just to confuse you. But I'm going to be shaking these 3 objects, and I'm going to be shaking them at the top with this particular motion. Now, the maximum response at the top, so the maximum my hand will see is 0.25 G, which is this peak here. The maximum of the output varies depending on the frequency. Now, what happens is in the low frequency range, we basically have very low stiffness. And I've also, as well as switching top and bottom, I'm switched from vertical to horizontal. Again, just to keep things interesting. So I'm shaking this back and forward at the top. This is a string and a pendulum. The string has very, very low stiffness horizontally. I mean, it has some tensile capacity, but if we're talking about the horizontal motion as a single degree of freedom system, it's very little stiffness. It has considerable mass, and so it has some inertia. And as I move this back and forward, this moves very little, maybe moves a little bit. not very much. So what happened is, in this low frequency range, I've put in an input motion, and the output motion has reduced. The peak response here is, so this red line is considerably lower than the input I put in. So this is representing the input motion at the top, and the motion at the bottom is reduced. And that is because it is so flexible that that motion is not transmitted down, and this has inertia resisting movement, so it doesn't move much at all. So you get this low frequency range where you basically get a reduction in the response. Then you increase the frequency, increase the stiffness, or at least increase the ratio between stiffness and mass, it starts to pick up, and we get to this kind of medium frequency range. And in this range, we get amplification. So if I think of like a plastic ruler, it's the same. I'm putting in the same motion, shaking it by the same amount at the top, but the end is flapping about like mad. It's moving far more than what I'm putting in, and that's because the stiffness relative to mass has gone up further. So we get this area of the spectra where we get an amplification. So we've still got the same input motion, but the output at this end is considerably higher, and that's because of the frequency of this system. And then we keep going, keep increasing the stiffness, keep increasing it further and further. This peaks and then starts to reduce. But unlike on this side, it doesn't go down to zero. It goes down to essentially the input motion. And what's happening here is we're getting very, very stiff. We're essentially getting to a rigid. I mean, nothing's truly rigid, but we're getting close to kind of infinite stiffness. And what happens here is I put in a motion at the top, and because this is so stiff, and at least relative to the mass, it's so stiff. The motion at the bottom is exactly the same. So this input motion at the top would be exactly the same input motion at the bottom, and the peak of this motion at the top is the same as the peak of the motion at the bottom. So it eventually plateaus, but it doesn't plateau at zero. It plateaus at the peak ground acceleration of the input motion. So this is generally the spectra shape you will see. I mean, like an actual spectra generated from a time history will not be as smooth and nice as this. There'll be ups and downs, but generally you'll get these zones. You'll get a kind of low frequency part where there's a reduction. You'll get a medium frequency where there's an amplification, and eventually it'll settle back down into this rigid response, which is essentially equal to the input. And this is often called the ZPA, zero period acceleration. If you remember, period and frequency are reciprocals of each other. So zero period means infinite frequency, i.e. rigid body. And at this ZPA, zero period acceleration, is when we essentially have the same as the input. So that's a response spectrum and the rough shape of it and why it is the shape it is. And it's all linked to the frequency of the system you're having, and that's therefore the response increases or decreases or stays the same as the input motion. Now, okay, so we have now looked at time histories, we've looked at response spectra. So generally, codes give response spectra as inputs. They define a nice shape. But there are times when we would want to do a time history analysis, even though they're more complex. They have more functionality. I think I was explaining to some of the other hosts at the start of the meeting. We use this on Hinkley and Sizewell for some more complex analysis for the generation of flow response spectra. For cases where we have base isolated structures with very high damping, we need to do a response spectrum analysis. But sorry, a time history analysis. I'm confusing myself. But we only have a response spectra. So how do we get, we've looked at going one this way to this. How do we get from a response spectra back to a time history analysis? And the answer is it's very difficult, and we can't really do it, or at least we cannot, there's no single correct answer. And I want to try and look at this very simple example and illustrate it that way. If you have three load cases, let's say we have dead and live, wind, and snow. And we have three different utilization ratios associated with that for the design of a beam. And I ask you, can you take these three utilization ratios and give me the peak of them? And it's really easy to do because you say, yeah, 0.8, 0.6, 0.9, the maximum is 0.9, that's the peak. This is similar to what we're doing with a time history and a response spectrum. We're taking a full input over time, and we're extracting the peak value, and that's fine because we use peaks for design, so that's all we need. If I tell you I have three load cases and the peak of those load cases is 0.9, what were the three individual values? It's impossible. You cannot solve this problem because you don't have sufficient information. One of these is 0.9, but maybe all three are 0.9. maybe it's 0.900, maybe it's 0.9, 0.5, 0.1. There's an infinite number of combinations of these which have a peak of 0.9. And it's the same issue we have with a time histories and response spectra. We have a response spectra, which is a plot of peaks. And we've been asking, what's the time history behind that response spectrum? The answer is there are an infinite number of time histories which all match that peak response. But how do we know which one to use? So this is the problem we face when going with from a response spectrum to a time history. And before I go to the next slide, how we deal with it, I'm going to use the same example to try and explain this. So how we deal with it is we do a couple of different, we look at a couple of different ones, all separate from each other. So if I wanted to know what these three values are, I cannot calculate them. But what I can do is I can look at maybe six combinations of those, 6 combinations of 3 values which meet this peak, but which all are sufficiently different from each other, such as like 0.1, 0.2, 0.9, 0.1, 0.5, 0.9, 0.5, 0.6, 0.9, 0.6, 0.8, 0.9. If I pick a set of values, some which are low, some which are high, some which are in the middle, some which are spread wide, some which are closely together. If I pick a series of these results, of these sets of values, which are all sufficiently different from each other, the hope would be that the actual input will be close to one of those. And that's essentially what we do as well with time histories when we're trying to match them to response spectrum. Because there's an infinite number and each one will give you different results, you cannot know there's not a single answer for what time history to use. So we generate several different time histories, all different from each other, all matching the spectra, and we run them all, and then we combine the results. So generally, when you're doing a time history analysis, you're not designing for a specific earthquake, designing for a couple of different earthquake inputs, trying to represent a broad range of earthquakes that may occur, and all matched to a particular peak value as defined by a spectra. And how many you do depends on the code, and it depends on what you're doing. I think if you're doing a non-linear analysis, it might be 7. If you're doing something quite simple, it might be 3. But that's essentially what we're doing. In terms of how you do it, I don't want to cover that, or I don't have time to cover that. But like I say, there is software that you can take a seed input, a real earthquake, and modify it to match a spectra. And the math for that is complicated, and I'm not going to cover it. But that's essentially what you do. But you try and get a set of time histories, and remember, each time history set is three inputs, and you would run them all and then combine them at the end. And again, it depends on the code how you combine them, whether you envelope them or average them. But just that's the principle of what you're doing. So yeah. So these are our 2 outputs, which I've covered now, and hopefully in sufficient detail that you're probably sick of hearing about them. At least you understand roughly what they are. We generally use response spectra. There are a couple of reasons for that. It's quicker, it's easier, it gives peaks, but we design for the peak. So we've lost a lot of information, but that information we wouldn't normally require. It allows simple hand calcs, as we'll see in a second. But the most important thing is a response spectrum is an infinite number of events. A time history is one event, and that one event will not be the event that your structure or system is subjected to. We cannot define an earthquake in that level of detail. So it's far better to design an earthquake in terms of a peak response. And that's why we use response spectra generally. And that's what the code will give us. That's how we'll define our input. And then we can later match time histories to that if we need. Okay, so my summary of where we've got to now. So we know what earthquakes are. We know about why they occur, and in the UK we're generally safe. Earthquake, the new information, we've got spectra or time histories. Time histories is a single event in a lot of detail and includes the variation with time. Response spectrum is a plot of the peak response varying with frequency, and it's an infinite number of events. And because of that, we normally use response spectra as our base input and then derive time histories to match them. Okay, now that's our input motion. So we know what an earthquake is. We know how to define an input motion for use in our analysis or design. So now I'm conscious of time. If I talk about types of seismic analysis, and I'm going to have to be quite quick, and so apologies for that. If I try and outline some of the principles, I think you can do research in your own time, or maybe you know it all already. If we can split them into static and dynamic, static is essentially where we are representing a dynamic event as a static force, i.e. a force that does not vary with time. And dynamic, we are considering the variation of the component with time. So we're considering that the fact that the force does go up and down or changes with time. In static, we're basically we're working out an equivalent, a pseudostatic force, and applying that as a permanent load to the structure and design of it. And then we have linear and non-linear, which is linear. So an elastic response. Non-linear, we have some plastic behavior, or we have contact, or we have some p delta, or some aspect that makes it non-linear. So if we talk about, just briefly, I've got one slide in each of these, I think, just to cover it. We'll start with the equivalent static, which is the simplest of them all, but is quite conservative. So in this case, we are taking an earthquake and representing it by a set of static forces. And then we can just analyze them the same as any other static force, the same as dead load, the same as wind load, or how we treat, I mean, wind load's not static either in reality, but we treat it as a static load, except for tall buildings. Anyway, sorry, I'm going off track. This, essentially here, we have our spectra, we know what the response is, how it varies with frequency. Reality is any building will have multiple modes of frequency. So there might be a mode here, maybe with 8 Hertz, which has a frequency of 0.4. There might be a mode up here, which has a frequency of 0.65. So different parts of the building will, or the mass in different parts of the building will experiencing different levels of acceleration. And that acceleration, and yeah, when you combine all those together to get the full response. But without splitting them up, in equivalent static, we're trying to do something very simple. It's basically a hand calc. We don't know what accelerations apply, but we know that the peak, that no accelerations will be greater than this 0.65. So we take 100% of the mass times the peak response, and we apply that as a static force. It is that simple. There is also a dynamic amplification factor you'll see in codes. That is to do with higher order modes. And for a simple structure, you can take that as 1. I think for base reactions, you can take it as 1. But for design of elements in more complex structures or structures with multiple supports, it's recommended to increase that. I think 1.5 is normally what you've done. So it's very simple, but it's very conservative. We're taking the maximum acceleration. We don't know if our modes are here or how much mass is actually activated at this acceleration, but we're assuming all of it is, and then we're increasing it even further potentially with this dynamic amplification factor, and then design for that as a static force. So good because it's simple, bad, it's quite conservative. But that's equivalent static. If we stay in the static case, so again, we're not looking at variations of force with time. We have a pushover analysis. Essentially, you apply a set of loads to a structure, a load pattern. You define a load pattern representing a particular event, say an earthquake, and you incrementally increase those or prorate those loads up until eventually the structure falls over. And what we're doing here is we are going beyond yield. So if you want an elastic design, you hit yield, you stop. That's the capacity of the structure. Push over, hit yield, you keep going. Like you'll get plastic hinges forming. You'll get failure of elements. You'll get buckling. As long as the load can redistribute somewhere else, you can keep pushing, and you eventually keep going until you push it over. Like pushover analysis, pushover. The advantage of this analysis is it tells you how much. Tells you 2 things: how much capacity you have over above the elastic limit. So once you get the onset of yield, in an elastic analysis, that would be you stop there. This is telling you how much further you can go. And typically, for a well-designed structure with a lot of ductility, you can go way beyond the initial onset of yield. So this will tell you how far you can go. It also tells you how the structure fails, which is also useful to know. If you want to strengthen something, you want to know where to focus any strengthening measures or where to do some redesign. It tells you that as well. But this is a pushover analysis, and we're still static here. We're still talking about line loads which do not vary with time. Then on to response spectrum analysis. If you remember when we talked about the equivalent static, it's a similar kind of principle, but here we're actually calculating the modes that occur in the structure. Each mode will have a mass associated with it, and we can then apply an acceleration to that mass and then add them all up together. Now we can only, or we combine them, sorry, rather than add them, combine them at the end. Now this can only be, because we are splitting it up into individual modes and assessing each mode individually, this can only be done, this can only cover linear elastic analysis. We cannot be plastic because we do not find the combined response until the end. Each individual component is assessed as a linear elastic, and the whole thing has to remain a linear elastic for us to be able to combine them. So this is limited to linear elastic analysis, so we're not going into any plastic range. But essentially, we have a simple structure which will have a response. That response can be made up of individual mode shapes, and we can resolve each of these individually and add them together. And that is essentially what we're doing. And I think go and do research on this on your own if you want. It's just important that you understand response spectrum analysis. This is what we're doing. We are splitting the structure up into modes, resolving each mode individually, and then combining them at the end to get the total response. And it's only for linear elastic. Time history is a more complex, or at least a more computationally intensive method. Essentially, you resolve this input and the design of the structure as a series of individual time steps where you solve this equation we saw before, so the mass acceleration, damping velocity, and stiffness displacement for each time step. So you start at 0, 0, nothing's moving, and then you have an input acceleration which causes some velocity, causes some displacement, and then for the next time step you have a variation in that acceleration, but you also have an initial velocity and you have initial displacement. So you're starting from a different position, but you resolve each time step in turn and you work your way all the way through to the end. And remember, we are doing this in 3 directions at the same time and combining them. And we are also, and our time steps may well be around 0.005 seconds. Obviously, the smaller you make the time step, the more accurate the results. But if this is a 40-second, if this is a 40-second event, and we're talking 200 per second, so yeah, 8,000. Sorry, 8,000 time steps to be resolved. It's quite computational, and if you remember again, for time history, we would not be doing this for a single time history. We'll probably have several time history sets. So again, there's a lot of work to do. But essentially, again, trying to keep this simple, so keep moving. We are looking at one time step. The output of that is our input for the next time step, and resolve them all the way through to the end. Okay, and then seismic design. So once we've got the analysis, we've got the forces, we need to think about seismic design. Again, a whole topic on its own. I think the main thing to note is it's not that different. So seismic design, if you think of Eurocode 8, it generally points you back to Eurocodes 2 and 3 for concrete and steel. So we have an element, we have forces in the element, and the designs for that, the moments, the shears, the axial forces are generally similar, or well, it's designed in the same way. There's a couple of additional principles we need to consider for seismic analysis, and the main one of those is ductility. So we're trying to, rather than just look at making the design stronger, we're trying to give the design flexibility or have failure modes that are ductile, not brittle, and which can dissipate the energy. So for example, if we have steel connections, if we can make the connections stronger than the beams that the moment hinge forms in the beam, and the beam is a plastic section, we can dissipate quite a bit of energy there. And so even if we do get local yield, we don't get collapse. So there's a big focus on that, but there's other aspects as well. I think the main thing is, though, the actual design of the elements, you're basically going back to Eurocode 2, Eurocode 3, Eurocode 5 for timber, and you are yes, it's the same engineering, it's the same principles. A couple other things I've noted here, but due to time, I'm just going to skip on. So yeah, go back to our summary. Various seismic analysis options. The most suitable method depends on the case, and for design, it's actually quite similar to standard design, but we really need to consider ductility in particular when we do that. In the last 5 minutes, I want to cover just 3 other points, which just covering them briefly, but I think you should be aware of them, just in terms of my trying to cover the fundamentals. First of these is damping. So we talked about damping a little bit, but damping is basically removing energy from the system. Higher damping is good, generally positive. I mean, it gets to a point where it actually can control the response, in which case it can be negative. But for any real damping that we have, generally increased damping is better. It's linked to the velocity. Damping constant, which is how we could define the damping, is these units here, kilonewtons seconds per meter, which might look odd, but it's just force over velocity. So because it's meters per second, the S comes back on the top, so kilonewtons seconds per meter. We typically don't define actual damping constants. We define damping as a proportion of critical damping, and critical damping is the damping sufficient to remove all the energy in a single cycle. So if you have like a pendulum and it's swinging back and forth and swinging less and less each time, it's damping that's removing that energy, which is decreasing the velocity each time. If you were to have critical damping, you would drop the pendulum and it would fall to the bottom and stop, and it wouldn't swing anymore. So it's a very high level of damping. And so we typically, it's difficult to achieve critical damping for the first thing, but also our damping are typically defined as a percentage of that. Damping also varies in how stressed the structure is, i.e. if the structure is behaving elastically, you'll get quite low damping. If the structure is deforming, creaking, groaning, some plastic behavior, that actually means you can use a higher level of damping, because that is removing more energy as it's deforming. So the damping may not be you might get different damping levels for the same structure depending on how hard it's working. So, okay, I've said this already. Damping is lower for elastically and higher for nonlinear. In time history, you can apply damping directly to elements. In a response spectrum, hopefully you remember this from when we talked about it, the damping is already included in the spectra. So when you generated a spectra, a response of a system, you chose a damping level. So when you're doing a response spectrum analysis, you do not define damping again. You basically define the response spectra to use, and that has damping already associated with it. And so if you want 5% damping or 2% damping, you're just essentially using a different response spectra as your input. That's how you're defining the damping. And you cannot assign it to individual elements, because you're assigning it to your response spectra input rather than to the elements themselves. You can assign different damping to different modes in a response spectra analysis. So you could, if you think about a mode, we have at 1 Hertz, we have an acceleration here. You can say at 1 Hertz, use the 10% damp spectra. At 2 Hertz, use the 5% damp spectra, which gives you a different acceleration. So you can assign different damping to different modes, but you cannot assign different damping to different elements, and any single element will be associated with multiple modes. So that's a limitation of damping in response spectra. And here are some typical values. I've taken it from ASC3, which is the American code for civil engineering of nuclear structures, just because that's what I'm familiar with. But you can see some typical damping levels, again, defined as percentage of critical. So that was topic 1. Topic 2, soil structure interaction. Everyone should be aware of this as well. A structure is not just sit in a fixed base analysis, it sits in a soil. If the structure is flexible and the soil is very, very stiff, then you do not need to consider SSI, because basically the response will be controlled by the response of the structure. So in this case, you can ignore soil structure interaction. However, for a more realistic case, there'll be some flexibility associated with the soil, and the structure will have a reasonable stiffness. And there may also be a response where the structure is actually moving with the soil. So the structure is essentially rigid and it's moving with the soil around it. In this case, the response of the structure is actually governed by the soil, and you need to consider that in your analysis. You cannot analyze the structure on its own. You need to have some representation of the soil, whether that's modeling the soil itself or representing the soil with springs, which can be frequency dependent or independent. But SSI is important. This is what you're doing. You're considering, does the soil affect my response of the building. If it does, I need to consider it. Otherwise, I'm missing a very important mode shape. And then we have soil structure interaction. So at SSI now we have triple SI. So if we think of our structure, so it has a response. The soil also has a response. We need to consider that. That's the SSI. But you can also have the case where you have a structure with a huge, heavy building next to it in close proximity. And effectively, the response of this whole system will be controlled by the response of this heavy structure. This is where most of the mass is. And this will be affecting the soil. The soil will be moving and responding associated with this. And this will basically be carried or impacted by the movement of this heavy structure. So we call this triple SI, where if you were to design this building using this model, you're actually missing an important mode of response, which is where the soil is being moved by the response of this heavy structure beside it. So triple SI, it's where you're looking at a smaller, lighter building next to a big, heavy one. In terms of the design of the big, heavy one, this small building will have no effect. So you wouldn't need to consider triple SI for this building as a result of having something lightweight next to it. It's more if you're looking at the lightweight building and there's a heavy building next to it. And then my last one, and just slightly over time, but we'll finish hopefully at 10:2, flow response spectra. I think everyone should be aware of this too. So we define an input motion. The input motion is defined at foundation level at the base, and it can be used for anything that sits on that base. It can be used for the design of a building because it's connected down to that foundation. It can be used for the design of equipment that sits at that foundation level. But as we saw from our response spectra, there's in the medium frequency part of the spectra, which is where most of our buildings will sit, there's an amplification of that response. That amplification generally increases with height. So an equipment at the bottom can be designed for this input motion. An equipment that sits on the 21st or the 29th floor here will actually be seeing a significantly higher input motion, and they cannot use the same input as at the base. So if we have an equipment that sits at one of these upper floors, what should we use to design it? Well, there are two ways you can do this. One is you use the base input, so you use the foundation input, but in your equipment, you ask your equipment designer to actually model the building. So they can use that input as long as they model everything between that level and their equipment. So although they're trying to design a bit of equipment, they're also having to essentially model and analyze all the building structure as well. So you can ask them to do that. They will tell you to go away, maybe less politely, and they wouldn't do it. And I'm not sure that many of them would have the capability to do it anyway. So that's that. Generally, we would do the second option, which is where the structural designer will actually generate spectra inputs for each floor. So we would take our base input, we would extract values at the floor of interest, and we'd give that to the equipment designer and say, okay, you're on the 21st floor. Here's the 21st floor spectra for you to use, and they can then consider their equipment in isolation. They don't need to consider the building. And that's it. Sorry, my summary. Earthquakes, it's the same points as before. Due to tectonic plates moving, largest earthquakes are at the edges. We have some in the UK. We define them in terms of input as a response spectra time history. Time history is one event. It includes time domain information response spectra is peaks only, and it includes infinite number of events that match that peak. We generally use response spectra as our input, and if we need time histories, we derive it from the response spectra, or we develop sets of them to match. We can do various seismic analyses with these inputs. A response spectral analysis splits the structure up into modes, and then for each mode there's a frequency. For each frequency there's mass associated with it, or for each mode there's mass associated with it and acceleration, and we can work out individual responses and then combine them. Time history, we are essentially resolving the equation of motion for each time step in turn using the previous time step as an input, and we work through the full event, and so we have a response. We have the full response over the event. Time history will be multiple time histories because we do not design for a single event. And for seismic design, it's not that dissimilar to normal design, but there are ductility requirements which set reinforcement, detailing arrangements and connection design, etc. So there are other aspects, but the most important is trying to ensure we have a ductile failure mode. Finally, on the last 3 points, damping is removal of energy. We define it as a proportion of critical damping. For response spectra analysis, it's defined in the response spectra itself, so that sets the damping. In time history, you can assign the damping to the elements, and you can vary it with elements. We also need to consider SSI, soil structure interaction. Its impact, even if it turns out we don't need to consider it, we need to have looked at it to make sure we don't need to consider it. But it's essentially where there are responses associated with deformation or movement of the soil, which need to be considered when designing the building. And triple SI is where there's a larger building next to a small one, and the response of the larger building is affecting the smaller building. And finally, for design of subcomponents, secondary structures, or equipment that sit on upper floors, we need to define a specific input associated with that floor for their design, and we do that by generating flow response spectra. And to get out of the flow response spectra, we take an input motion, which has to be a time history. You cannot take, sorry, I should have mentioned this, you cannot take a response spectra at the base and turn that into a response spectra at a floor. You need to take the response spectra at the base, convert it into a set of time histories, run a time history analysis, extract time histories at the floor, and then convert them to response spectra. It's one of the areas where we do need to do a time history analysis. And that's it. So I hope that was useful. I hope it was simple enough that it was a decent introduction. And yeah, any easy questions, note the important word in the middle.